ವಿದ್ಯಾರ್ಥಿಗಳೇ, ಇದು Determinants part 10. In this session, I am going to discuss adjoint of a square matrix. ಹಿಂದಿನ ಸೆಷನ್ ಅಲ್ಲಿ ನಾವು ಮೈನರ್ ಅಂಡ್ ಕೋಫ್ಯಾಕ್ಟರ್ ಆಫ್ ಅನ್ ಎಲಿಮೆಂಟ್ ಈ ಬಗ್ಗೆ ಡಿಸ್ಕಸ್ ಮಾಡ್ತಾ ಇದ್ವಿ. ಈಗ ಅದೇ ಕಾನ್ಸೆಪ್ಟ್ ಅನ್ನು ಇಟ್ಕೊಂಡು ಮುಂದುವರಿಯುತ್ತಾ ನಾವು ಅಡ್ಜಾಯಿಂಟ್ ಆಫ್ ಎ ಮ್ಯಾಟ್ರಿಕ್ಸ್ ಈ ಕಾನ್ಸೆಪ್ಟ್ ಅನ್ನು ನಾವು ಡಿಫೈನ್ ಮಾಡ್ತಾ ಇದ್ದೀವಿ. Now consider the matrix A is equal to matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. Now we know that the minor of an element A11 is the determinant of the elements obtained by deleting the first row and the first column, that is A22, A23, A32 and A33. Similarly, suppose if you want to find out the minor of an element A23 is the determinant of the elements obtained by deleting the second row and the third column. So when you deleting the second row and the elements of the second row and the third column, the remaining elements are A11, A12 and A31, A32. Now we will define the cofactor of an element. So how to define the cofactor? Cofactor of an element, here cofactor of A11 is minus 1 to the power of 1 plus 1, sum of the suffixes of A11 into minor of an element M11. So we define this denoted by M11 and this is denoted by M23. And the cofactor of an element is denoted by capital letter A11. So minus 1 to the power of 1 plus 1 into M11. So we have the minus 1 to the power of 1 plus 1. 1 plus 1 is even number, therefore it is plus, and M11. So expansion of the determinant of A22, A23, A32, A33. This is A22 into A33 minus A32 into A23. Similarly, next the cofactor of the element A23, is minus 1 to the power of 2 plus 3 into determinant of the element, that is A11 into A32 minus A31 into A12. So we have minus 1 to the power of 2 plus 3. 2 plus 3 is odd number, therefore it is minus of A11 into A32 minus A31 into A12. So the cofactor of the element gives the sign. Now for all these elements, if we find out the cofactors of all the elements and this matrix is replaced by all the cofactors, all its cofactor, then we define cofactor matrix. It is denoted as the cofactor matrix is the matrix obtained by taking the cofactors of all the elements. So cofactor of A11 is denoted by capital A11. This is A12 and A13. This is A21 and A22, A23, A31, A32, A33. So this is the cofactor matrix. Now we define the adjoint of the matrix. The adjoint of the matrix is denoted by adjoint A is the transpose of the cofactor matrix. Transpose of cofactor matrix. So that is, the transpose of the cofactor matrix is A11, A12, A13 and A21, A22, A23. So A31, A32, A33. So this is the adjoint of the matrix. So we define the adjoint of the square matrix. So the adjoint is defined only for a square matrix. The adjoint of a square matrix A is equal to Aij of order n by n is the transpose of the cofactor matrix, which is obtained by andre cofactor matrix ಹೇಗೆ ಬರುತ್ತೆ ಅಂತ, which is obtained by replacing all the elements by its cofactors. So this is an adjoint of the matrix. So this is very important to define the inverse of a matrix. Now we have taken only for 3 by 3 matrices. Now let us take for 2 by 2 matrices. Now consider this matrix A11, A12, A21, A22. Now for the square matrix, we know that, let's take the minor. So minor of an element, minor of A11 is A22, because leaving the elements of first row and the first column, because A11 lies in the first row and the first column. So leaving the elements of first row and the first column, we have the remaining elements as A22. So now cofactor of A11 is minus 1 to the power of 1 plus 1, that is 1 plus 1 into minor of A11 is A22. So it is A22. 1 plus 1 is even number. Now let's find out all the cofactors. Minor of A12 is leaving the elements of first row and the second column. We have the remaining element as A21. This is the element A21, leaving the elements of first row and the second column. So therefore cofactor of A12, now we can write directly sign. So 1, 2, A12, sum of the suffix is odd number. So 1 plus 2 is 3, therefore it is minus A21, that is the minor of the element A12. Now minor of the element A21 is A12, leaving the elements of the second row and the first column, we have the remaining element as A12. So therefore cofactor of A12 is equal to, so 1 plus 2, again this is A21, sorry, this is 2, 1, this is 2 plus 1, 2 plus 1, 2, 1. Cofactor of A21 is 2 plus 1 is 3, therefore it is also minus A12, that is the minor of the element A21. So minor of the element, last element A22 is equal to, leaving the elements of second row and the second column, we have the remaining elements as A11. So therefore cofactor of the element cofactor of the element A22. So here 2 plus 2 is even number, therefore it is plus. The minor of the element A22 is A11. Now I will replace. So what is the cofactor matrix now? So cofactor matrix of A given by cofactor matrix of A is cofactor of the element is A22, this is minus A21, this is minus A12, this is A11. This is the cofactor matrix. We know that adjoint of a matrix denoted by ADJ, adjoint A, is the transpose of the cofactor matrix. Therefore, this you can write the transpose of this, changing the rows into column, A22 minus A21 and minus A12 A11. This is the adjoint of the matrix. So therefore, what is the original matrix? A is what? A11, this is A12, A21, A22. We can find the adjoint of the square matrix easily. Just observe and compare these two matrices, adjoint of A and A. So in this case, so we have A22, A11. Observe this, A22, A11. The elements of the principal diagonal here are interchanged. So here the elements of the principal diagonal in the adjoint of A are interchanged from the original matrix A. Now, what about the other diagonal? The elements of the other diagonal are same but changes in its sign. Changes in its sign. So we can find the adjoint of the square matrix, that is a matrix of order 2, as, so for a square matrix, square matrix of order 2, adjoint of A is obtained by first one, changing the interchanging the elements of the principal diagonal, interchanging the elements of the principal diagonal and changing the, second thing is changing the sign of the other diagonal. Changing the sign of the other diagonal. So for example, if we have a matrix, suppose A is a matrix 1, 2, 3, 4. Adjoint of A is obtained by interchanging the elements of the principal diagonal. This is 4, 1, because this is elements of the principal diagonal are 1, 4. Changing the sign of the other diagonal, minus 3, minus 2. Easily we can find out. Suppose if A is a matrix, that is 2, 3, minus 4, minus 6. Then adjoint of A is obtained by changing the elements of the principal diagonal minus 6, 2, and changing the sign of the other diagonal. Here is minus 4, it is plus 4, minus 3. So this is how we get the adjoint of the matrix of order 2. Similarly, we can find by replacing the elements of the cofactors for a matrix, we can find the, by taking the transpose of the cofactor matrix, we can find the adjoint of a matrix. And it is very important to remember the sign of the cofactors for matrix of order 3. Matrix of order 3. So we have A is a matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. So the sign of the cofactors for this is, we can take, for the, to define the cofactor of the element, we must know this A11. The suffix lies in the first, suffixes are 1 1, therefore it is 1 because sum of the suffix is even. So 1 plus 2, here this is 1 plus 2, suffix is 1 2, so sum of the suffix 1 plus 2 is odd number, therefore it is minus. So it is 1 plus 3 4, it is plus, and 2 plus 1 3, it is minus, 2 plus 2 4, it is even number, it is plus, 2 plus 3 5, it is odd number. Similarly, we have plus and minus plus. So to write the cofactors of the elements, it is better to know the sign of the elements before finding the cofactors. So now consider one problem. Find the adjoint of the matrix. Adjoint of the matrix of order 3, matrix 2 minus 1 3 minus 1 4 2 0 minus 3 1. So now the given matrix, let's take, let A is a matrix 2 minus 1 3 minus 1 4 2 0 minus 3 1. Now let's find out the cofactors of all the elements. So let's take the cofactor of all the element A11 is equal to, leaving the elements of the first row and the first column, determinant of the, so A11, let us write the sign directly, 1 plus 1 is even number, it is plus, I am writing. So determinant of 4 2 minus 3 1, so therefore it is 4 minus 6, so 4 plus 6 is 10. So then let's take A12, the cofactor of the element minus 1, so 2 is over, so 1 plus 2 is odd number, therefore it is minus, determinant of, leaving the elements of first row and the second column, the determinant of the remaining element minus 1 to 0 1. Therefore expanding the determinant minus of minus 1 into 1 minus 1 minus 0. So minus of minus 1 will become plus 1. So A11, A12, then A13 is 1 plus 3 is even number, therefore it is plus determinant of leaving the elements of first row and the third column, we have the remaining elements as minus 1 4 0 minus 3. So this is plus into minus 1 into minus 3 is 3 minus 0, therefore it is 3. Now let's take the cofactors of the second row. Now A21, 2 plus 1 is odd number, therefore it is minus. Then leaving the elements of second row and the first column, the determinant of the elements minus 1 3 minus 3 1. So this is equal to minus of minus 1 minus of 3 minus 3 into 3 is minus 9. Okay. So therefore this is minus of minus 1 minus of minus 1 plus 9, minus 1 plus 9. So this is equal to minus of minus 1 plus 9 is minus 8. Then A22 is 2 plus 2 is even number, it is plus determinant of, that is the cofactor of the element 4. So leaving the elements of second row and the second column, the determinant of the remaining elements are, leaving the elements of second row and the second column. So that is 2 3 0 1, that is equal to 2 into 1 2 minus 0, that is equal to 2. Then A23, 2 plus 3 is odd number, therefore it is minus determinant of. So leaving the elements of second row and the third column, we have the remaining elements 2 minus 1 0 minus 3. So 2 minus 1 0 minus 3. So this is minus of 2 into minus 3 minus 6 minus 0, it is minus of minus 6 is plus 6. Then A23 is over. Okay, the second row cofactors to second row is over. Now let's come to the third row. A31, 3 plus 1 is even number, therefore it is plus determinant of, leaving the elements of third row and the first column, the elements are minus 1 3 4 2. So minus 1 3 4 2. Writing this, minus 1 into 2 minus 2 minus 12, it is minus 15 minus 14. Then A3132, so 3 plus 2 is odd number, it is minus determinant of. So leaving the elements of the third row and the second column, observe the matrix A, the elements are 2 3 minus 1 2, 2 3 minus 1 2, and that is equal to minus of 2 into 2 4 minus of minus 1 into 3, so minus 3. So that is minus of 4 plus 3, it is minus 7. Now A33, 3 plus 3 is even number, so it is plus. So leaving the elements of the third row and the third column, so the remaining elements are 2 minus 1 minus 1 4. 2 minus 1 minus 1 4, taking the determinant of these elements, so plus 8 minus 1 into minus 1 plus 1, so 8 minus 1 is 7. So now let us write the cofactor matrix. Cofactor matrix. Writing cofactor matrix, that is first A11 10 1 3, A11 A12 A13, so 10 1 3, so 10 1 3. Now the elements of the second row, cofactors elements of the second row, minus 8 2 6, minus 8 2 6. Then third row, minus 14 minus 7 7, minus 14 minus 7 7. This is the cofactor matrix. Now the adjoint of A is the transpose of this matrix, that is 10 1 3, then minus 8 2 6, then minus 14 minus 7 7. So this is the adjoint of the matrix. So we can write the adjoint of A directly by taking the elements directly column wise. Okay. Instead of writing vertically, horizontally, if you write vertically, you will get the adjoint of A directly. So this is how we can find the adjoint of a matrix, by using minor and cofactors of the elements. Now consider some of the results related to the adjoint of the matrix. Adjoint of a matrix. Now let's consider as a theorem. Theorem 1. If A be any given square matrix, any given square matrix of order n, then A into adjoint of A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I, where I is the identity matrix of order n. So this is the property we are taking. Let us verify this theorem, taking the matrix generally. Now let's verify this verification. Now consider the matrix A as A11, A12, A13, A21, A22, A23, A31, A32, A33. So then we know that adjoint of A is the transpose of the cofactor matrix, that is writing the cofactors of the elements vertically A11, A12, A13, A21, A22, A23, A31, A32, A33. So this is the adjoint of A. Now consider A into adjoint of A. A into adjoint of A is equal to writing the elements A11, A12, A13, A21, A22, A23, A31, A32, A33, and writing the adjoint capital A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, so writing the product of these two matrices, both are 3 by 3 matrices, they are comfortable for multiplication. So I am going to multiply this. So taking the rows for the first matrix, column for the second matrix, we will write first row and the first column. Sum of the products of the elements is the first row and the first column. First row, first column. A11 into A11. Recall what you multiply under matrix multiplication. A11 into A11, A12 into A12 plus A13 into capital A13. Then first row and the second column for in the second matrix. So therefore this is 1, and A11 into capital A21 plus A12 into capital A22 plus A13 into capital A23. Next, first row and the third column, that is A11 into capital A31 plus A12 into capital A32 plus A13 into capital A33. Then second row and the first column, A21 into A11 plus A22 into A12 plus A23 into A13. Then second row and the second column, A21 into A21 plus A22 into A22 plus A23 into A23. Now the second row and the third column, A21 into A31 plus A22 into A32 plus A23 into A33. Now taking the third row and the first column, A31 into capital A11 plus A32 into capital A12 plus A33 into capital A13. Now second row and the second column, A31 into capital A21 plus A32 into capital A22 plus A33 into capital A23. Now A31 into capital A31 plus A32 into capital A32 plus A33 into capital A33. So completing the matrix. See, in this multiplication, sum of the products of the elements, here we can observe that these elements A11, sum of the products of the elements of the rows with their corresponding cofactors. We have seen in the earlier concept, sum of the products of the elements with their corresponding cofactor is the value of the determinant. Here this is the value of the determinant. So this is determinant of A, this is determinant of A, this is determinant of A by the previous results. But sum of the products of the elements with the corresponding cofactors of the other row is 0. This is all are 0. Here we have all are 0. So they are equal to 0. This is 0, equal to 0, 0, 0, 0. So from these results we conclude that this is equal to determinant of A 0, 0, 0 determinant of A 0, 0, 0 determinant of A. So the elements of the principal diagonal are determinant of A. So taking the common factor means 0 is multiplied by determinant of A, because this is the scalar multiplication, this is also determinant of A. You can take like this, determinant of A is 0, again determinant of A. So we can conclude this is also into determinant of A, into determinant of A. So we can conclude this is a scalar multiplication of the matrix by determinant of A, that is unit matrix 1 0 0 0 1 0 0 0 1. So when you multiply determinant of A to this unit matrix, you are getting the same matrix. So we got the result determinant of A into, this is the unit matrix, that is the identity matrix, determinant of A into I. So from this conclusion we arrive the result that A into adjoint of A is equal to determinant of A into I. Similarly, adjoint of A into A, we are also getting determinant of A into I. So from this we conclude the very important concept that A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I. So this is one of the important concept. From this definition we will arrive the result, that is for the inverse of a matrix. And from this result we arrive the one of the very important thing. So as a note you can take, so we have adjoint of A into A is equal to determinant of A into I. So how do you write this determinant of A into I? This is, just now we have seen determinant of A into 0 0 0 determinant of A 0 0 0 determinant of A. See, observe this. This is determinant of A 0 0 0 determinant of A. So this is, we have written determinant of A multiplied by identity matrix. Now taking the determinants on both sides, taking determinants on both sides. So this is adjoint of A into A is equal to determinant of, so we have to take the determinant of this matrix, that is determinant of A 0 0 0 determinant of A 0 0 0 determinant of A. So now here this determinant, this is the determinant actually. So we can take in the determinant that we know if there is any common factor in any row or column, that can be taken outside the determinant. So from the first row we have determinant of A as a common factor, determinant of A. Similarly for the second row we have determinant of A as a common factor, determinant of A. And even for the third row we have determinant of A as a common factor. So that can be taken outside the determinant. So 1 0 0 0 1 0 0 0 1. So this is the identity matrix. So we have determinant of A into determinant of A cube, and determinant of identity matrix is 1. So we have the result that adjoint of A, determinant of adjoint of A into A is determinant of A cube. So now from this we have one concept that is to be noted here, that is determinant of AB. If we multiply any two matrices and taking the determinant of AB, we have the result determinant of A into determinant of B. This can be proved by taking the A and B generally, or we can take the examples that, so I will take this later. So let's assume that determinant of AB is determinant of A into determinant of B. Using this result, now I am going to prove this. So determinant of adjoint of A into A is written as adjoint of A is also matrix. So this is in place of A and A is in place of B. So determinant of adjoint of A into A can be written as determinant of adjoint of A into determinant of A is equal to determinant of A whole cube. So we have determinant of adjoint of A into determinant of A whole cube. Now we can write determinant of adjoint of A is equal to determinant of A whole cube divided by determinant of A. So this is determinant of A whole square. So we have determinant of adjoint of A is determinant of A whole square. Here A is a matrix of order, square matrix of order 3. Then we have determinant of A square. So from this we come to the general conclusion that in general if A is a square matrix of order n, then determinant of adjoint of A is equal to determinant of A to the power of n minus 1. Here observe that it is a matrix of order 3, therefore it is determinant of A square, 1 less than that. So if A is a square matrix of order, then determinant of adjoint of A is determinant of A to the power of n minus 1. So this is very important result. And here we have, you have observed that we have used this concept, that is the determinant of the product of the matrices, that is also as a theorem we can take as a theorem 2. The determinant of the product of matrices is equal to the product of their respective determinant. Respective determinants. that is determinant of AB is equal to determinant of A into determinant of B, here where A and B are square matrices of same order. So here these results we have given in our textbook. There is given without proof, so we can take it directly. Of course, I will verify by taking 2 by 2 matrices, especially if we take A is a matrix, that is 2 1 3 1, and B is a matrix, that is 1 0 0 1. I am taking this. So let's take this 2 0 2 like this. What is this? Determinant of A is that is 2 minus 3, it is minus 1. Determinant of B is 2 into 2 is 4. Now let's multiply this AB. So AB is that is 2 1 3 1 and 2 0 0 2. So taking the multiplying this rows and columns. So 2 into first row and the first column, 2 into 2 is 4 plus 0. First row and the second column, 2 into 0 0 plus 2. Then second row and the first column, 3 into 2 6 plus 0. And second row and the second column, 3 into 0 0 plus 1 into 2 2. So we have this 4 2 6 2. Taking the determinant of AB is equal to 8 minus 12. It is equal to 8 minus 12 is minus 4. See, observe that this is equal to determinant of A into determinant of B, because here determinant of A into determinant of B is minus 1 into 4 is minus 4. So that verifies the result. Determinant of AB equals determinant of A into determinant of B. We can check this for 3 by 3 matrices also. So here in this problem we have taken, observe, determinant of adjoint of A into A. This is also matrix. This is also matrix. So this is also matrix. A into adjoint of A is determinant of adjoint of A into determinant of A is equal to determinant of A cube. We have used exclusively this theorem. Suppose if in this case, if A is a square matrix of order n, determinant of adjoint of A, determinant of A to the power of n minus 1. Suppose if A is a square matrix of order 2, then determinant of adjoint of A is 1 less than order this 2 is determinant of A. If A is a square matrix of order 2, the determinant of adjoint of A is determinant of A. If A is a square matrix of order 3, then determinant of adjoint of A is determinant of A square. So this is the general result. Determinant of adjoint of A is determinant of A to the power of n minus 1. So now remember this note, for 2 by 2 matrices, 2 by 2 matrix, determinant of adjoint of A is determinant of A. For 3 by 3 matrix, determinant of adjoint of A is equal to determinant of A square. For matrix of order n, for by n matrix, determinant of adjoint of A is equal to determinant of A to the power of n minus 1. So this results sometimes can be asking for 1 mark. Suppose the question may be asking like this. Suppose if determinant of A is equal to 5, Find the determinant of adjoint of A. Find determinant of adjoint of A if A is a matrix, square matrix of order 3. So from this we conclude that determinant of adjoint of A, if A is a square matrix of order 3, then determinant of A square. So determinant of A is 5, so 5 square, this is equal to 25. Suppose if they are asking square matrix of order 2, this is determinant of A, just 5, like that. So sometimes if the question may be altered using the inverse of a matrix, so that to define the inverse of a matrix we will take those sessions in the next video. So to using the adjoint of a matrix we will define the inverse of a matrix using the theorem A into adjoint of A is equal to determinant of A into I. So please go through the minor cofactor of an element and adjoint of a matrix to understand the next concept, inverse of a matrix. Thank you.